and welcome to Dot Tutoring. Today we'll be going over a subject many students find very daunting, dynamic programming, but I'm here to break it down into easy, digestible chunks. But before we jump into how to do dynamic programming, let's talk about what it is. The best way I've found it described is as efficient brute force. And essentially this means that we're trying every possible combination, but we're doing it very efficiently. And so we're not recalculating anything that would lead to exorbitant runtimes like exponential. Because for example, in this case, if you were to actually brute force this, you would end up with a 2 to the n runtime, but we have an even better one. So let's talk about what this problem even is. This is a very common dynamic programming introduction problem, and it's called longest increasing subsequence. And so today, as I go through the steps of dynamic programming, I'm going to at the same time be walking through how to solve this problem using those steps. And I think that'll really tie it all nicely together. And so what this problem is given an array of integers, and we're labeling this array A, and it has n integers, return the length of the longest increasing subsequence. Integers is not a necessity, and uniqueness is also not a necessity, but it doesn't matter. Either of those things could be easily changed. So let's look at this problem, this example, and see how we can alter this. So given this problem, what numbers are we going to pick? So I can pick 1, 2, 4, 8. That's a subsequence of increasing value, but that only has a length of 4. Let's see if we can improve this. If I pick 1, 2, 4, 5, 6, 9, and I skip over 8, then I end up with a length of 6. And I've actually already done the math for you, so I can guarantee that this is the longest increasing subsequence. And in this case, it's unique, which makes it even more interesting. So our length is 6. And for this problem only, we're going to just be focusing on the length and not the actual subsequence. You can backtrack and figure out the length fairly simply, but it is more work that needs to be covered. So let's move on to the actual steps. All right, our first step is the hardest one in my opinion. It is the big leap you need to take before everything else goes smooth sailing from here. Let's discuss the English definition. This very formulaic, but it's a little bit more difficult to come up with. We go as follows. Let some function name with parameters denote the subproblem definition based on these parameters. So let's see how we would apply this to our longest increasing subsequence. So I'm going to start off as per usual, let lis, and I'll get back into what the parameters we're going to choose. Denote, well, now I have to acknowledge the subproblem. What is our subproblem? Well, we're trying to find the longest increasing subsequence. So let's find it. Denote the longest increasing subsequence of some value, right? And so what are we trying to find? Increasing subsequence of what? Well, we want to find the longest increasing subsequence of some area. And so we're going to keep track of the current index we're looking at, and that's what I'm labeling as I. And that current index is going to be the index we're looking at. Let lis I, comma something, denote the longest increasing subsequence of a I through n, given that, well, I'm looking at this subproblem, right? I'm looking from ai to n, but I need to know the last index taken, the last element taken, in order to ensure that the next element I pick does not go below that, right? We don't want to pick an element that is below the last element picked. So what does that mean? If I picked 8, I don't want to pick 5 now, because then that's not a valid increasing subsequence. So what am I going to do? I want to keep track of this index that I've picked, j, given that a of j was the last element taken. So we've completed our English definition, and we have it based on the parameters. We figured out what parameters we need to acknowledge and everything else. Now let's move on to the second hardest step. We've just completed the first one, so good job, everyone. Our recursive definition. Our recursive definition, depending on the problem, there are exceptions, but generally this can be very, very formulaic. Basically, all we need to do is get our base cases, figure out what our base cases are, and then our general cases. Sometimes we'll have more. So let's talk about this. This is all coming from the previous step. So LIS of ij, right, is equal to, we have our base cases and we have our general case. So what's our base case? Our base case is the most trivial thing you can come up with. What is the most trivial case? Well, if our index is out of bounds, if our index is greater than n, then what happens? Well, I'm returning 0, right? I don't care. Like, I can't pick an element that's not in the array. So I'm done. Once I've exceeded the limit of the array, I'm done. Now, let's consider the more general case. Well, what are our two cases when we're in the more general case? The first case is that the element that we are seeing that we're currently at is less than the last element that we've picked. So if AI is less than AJ, well, in this case, can I pick it? No, right? I can't pick AI if I already picked AJ. In this case, what happens? I just return I plus 1, comma j. Why? Well, the last element taken was j, right? I can't change that because I didn't pick a new element. And well, we know that I is not a valid index for this specific subproblem, so we have to move on. Now, let's consider the second case. This is where the actual interesting stuff in dynamic programming comes in. What happens otherwise? So I'm going to say otherwise, or we're going to write if AI is greater than or equal to AJ. Something to note about dynamic programming is that we really want to be the least clever that we can be. Like, we want to make sure that we're covering every single case, even if it may seem redundant to you. Why? I'll explain this in a second. So let's talk about what we do in this case. Well, this is the biggest rule in recursive definition. You want to consider what happens if you take it and what happens if you don't take it. So we're going to take the maximum over these two cases, right? Because we're trying to find the longest increasing subsequence. What happens if I take it? If I take it, then I add 1, right? Because I've now increased the number of elements that I've taken. And I recurse on LIS I plus 1, right? Because I'm moving the needle forward. I've moved another element forward. And comma, I. I is the last element that we've taken. And so therefore, that's why we're keeping track of that. Okay, well, what happens if I don't take it? If I don't take it, it's the same exact case as the above one, right? As this one. Because I'm not taking it. And that's what happened there too. So LIS I plus 1, comma j. And we've officially finished the two hardest steps in the entire dynamic programming. Everything from here on out is very formulaic. But let's quickly just discuss why we have to consider both of these cases. Well, if I didn't consider that, and I just said, oh, if the number is greater than the last element taken, well, then I'm going to pick 8. And if I pick 8, then we know that I'm going to end up with a subsequence of 5, right? 1, 2, 4, 8, 9, which is not the longest subsequence, and we can get a better one. So that's why we don't want to be clever. We want to make sure we're considering all of our options. So let's move on to step 3, evaluation order. Again, dependent on the last step. Everything in dynamic programming is dependent on the previous step, except for the last one. That one's a little bit special, but let's discuss what our evaluation order is. Well, this is the order in which we're going to memorize our array. It also includes what we're going to memorize. I didn't just say memorize wrong. It's actually a term. Look up memorization. But, well, we have to pick an array. We have to get a size. And again, very formulaic. What do? We look at the number of parameters we needed for our thing. And for almost every case, it's just going to be, we need one dimension to cover the I and one dimension to cover the j. That means we're going to have an n by n array. Why? Because I can span between 1 to n, and j can span between, well, j is a little special. J is going to be spanning between 0 and n minus 1, and I'll explain a little bit more in detail why that is true, but just for argument's sake, consider it true. And both of these have order n, so that is not a problem. And so now I'm going to name my array LIS, and I'm going to give it 2 dimensions of size n, which means that overall, my dimension, I have a 2D array of n by n. Now, let's discuss our actual evaluation order. Well, let's consider this to be the I and this to be the j. Let's go back to the original problem, to our recursive definition. If I is greater than or equal to n, then it's 0. So all I need to do in this case is, assuming this is I equals n, right? I didn't want to draw out an n by n matrix because n is undefined. But if this is I equals n, then all of these columns will be 0, right? And so that's our first step. We're just filling out the first row in zeros. Then let's look at our next step. Well, LISIJ is dependent on LISI plus 1 comma j, which means that in order to know this element right here, in order to know this element, I have to know something in the column right below it, or in the row right below it. So I have to know LISI plus 1, which is in the row right below it, comma j, and so that should be this element right here. So that's one case. So we're seeing that LISIJ is dependent on the row right below it. And for the next case, LISI plus 1 comma I, well, I also have to know, in this case, I is the same. So let's actually consider a separate case. Let's look at if this is our I. Well, in this case, I also have to know this case, right? And so all we're seeing is that the row right above it is dependent on the row below it. Yeah. And so that means that when we fill out this array, we're going to want to fill it out in reverse order. So our first for loop, our outer for loop, is going to be for I equals n to 1. And our second for loop, so this is where we're going to iterate over j's, you'll notice that I'm already going to have filled out the entire row. So it doesn't actually matter in which order I fill out j, because I is the only one that's really dependent. But we can, on itself, that is, j depends on like the previous row, but I depends on itself. So for j, just for simplicity's sake, I'm going to keep it in the same direction, but you can do it in the reverse side also. So j n to 1. And that's how we do it. And actually this follows a really simple rule where if you're adding, then you're going to go in the reverse direction. And if you're subtracting, then you're going to go in the normal direction. But hopefully you